Specification for Foundation Fieldbus Part 4. Physical Layer. The physical layer of Foundation Fieldbus defines how digital signals are transmitted across the physical medium, serving as the foundational infrastructure upon which the protocol stack operates. It includes specifications for signal type, voltage levels, cable construction, termination, power delivery, and intrinsic safety considerations. This layer enables simultaneous digital communication and power transmission over a single, two-wire shielded twisted pair, simplifying field wiring while ensuring high signal integrity. The most widely used medium in Foundation Fieldbus is the 31125 kbps wire-based physical layer, standardized under IEC 61158-2. Though this rate may appear modest compared to Ethernet standards, it is optimized for hazardous environments and low-power teledetect high-integrity communication. This allows for field devices to be bus-powered, mirroring the two-wire philosophy of 420 mA analog systems while transmitting digital signals with advanced data capabilities. Fieldbus uses Manchester encoding for signal transmission. A logical 1 is encoded as a falling edge in the middle of the bit interval, and a 0 is encoded as a rising edge. This method ensures clock synchronization between transmitter and receiver and supports robust transmission even over long distances or in electromagnetically noisy environments. The signaling voltage is superimposed on the DC power supply, allowing simultaneous power and data over the same cable. To ensure stable signal integrity, each end of the Fieldbus segment must be terminated with a 100 ohm resistor in series with a 1 megafarad capacitor. These terminators match the cable's characteristic impedance and maintain signal shape by preventing reflections. The terminators are always installed, one at the power supply and the other at the furthest point on the segment or junction box. Under no circumstances should terminators be omitted or duplicated on a single end. The physical segment consists of a trunk and multiple spurs. The trunk is the main cable carrying signals and power between the host system and field junction boxes, while spurs are short branches connecting individual devices to the trunk. According to IEC guidelines, a standard Type A cable, 18 AWG, shielded twisted pair, allows for a maximum trunk length of 1,900 meters and a combined spur length, depending on the number of connected devices, up to 120 meters for 12 or fewer devices. Power to the segment is supplied via an isolated power conditioner. This unit includes an impedance element, usually an inductor network, that separates high-frequency communication signals from DC power. The conditioner must provide a minimum of 9 volts and not exceed 32 volts at the device terminals, with sufficient current capacity for all connected field instruments, typically 350 to 500 milliamps. The power supply must comply with ripple and noise constraints to avoid interference with signal modulation. The physical layer also enables bus-powered operation, meaning field devices draw their operating power directly from the signal cable. This simplifies wiring, eliminates the need for separate power sources and ACD, and is especially advantageous in hazardous or space-constrained areas. Each bus-powered device is typically limited to 20 milliamperes current draw to preserve system-wide load balance. For high-power instruments, local power supply with galvanic isolation may be required. Intrinsic safety, IS, is a major design criterion for Fieldbus installations in hazardous areas. Fieldbus supports several IS models such as FISCO, FNICO, and entity-based designs. In these configurations, the total energy in the segment is strictly limited via safety barriers or isolators to prevent spark ignition in explosive atmospheres. Devices, cables, and terminators in IS loops must be certified to comply with relevant safety standards, e.g. IECEX, ATEX, FM. Signal quality is maintained through strict wiring practices and segment rules. Type A cable is recommended for trunk lines due to its shielding and consistent impedance. Shield continuity must be maintained and connected to ground at a single point only to prevent ground loops. Cable installations must observe minimum bend radii, spacing from power lines, and appropriate segregation from other electrical circuits. To support long-distance installations or high-availability networks, repeaters and segment couplers can be used. Repeaters regenerate and retransmit the signal to extend distance or branch additional spurs. Segment couplers electrically isolate segments and support configuration of complex topologies. All couplers must preserve protocol timing and be compatible with segment current and voltage limitations. In summary, the physical layer of Foundation Fieldbus establishes a reliable, low-power, noise-tolerant communication and power delivery platform. Its standardized implementation reduces installation complexity, enhances signal integrity, and ensures safe operation in hazardous industrial environments. When implemented in accordance with certified wiring rules and electrical guidelines, it enables a high-performance digital backbone for process control applications. Specification for Foundation Fieldbus, Part 5. Data Link Layer. The data link layer of Foundation Fieldbus plays a critical role in managing how data is transmitted, prioritized, and scheduled across the shared communication medium. It ensures that only one device transmits at any given time, controls message sequencing, regulates communication priorities, and maintains synchronization across all nodes on a segment. It transforms the physical layer's raw signal pathway into a structured and deterministic network suitable for distributed control. At its core, the data link layer implements a token-based medium access control (MAC) mechanism. All devices on a Fieldbus segment share a single physical medium, so only one device is permitted to transmit at a time. The token is a permission signal managed by a special device called the Link Active Scheduler, LAS, which arbitrates access to the bus and ensures fair and timely communication among all connected devices. The LAS maintains a rotating schedule, distributing tokens to each device in sequence. Devices may only transmit when they receive the token. This ensures deterministic behavior, a requirement for real-time process control. The LAS also issues compel data CD messages to prompt publishing devices to transmit scheduled data. Devices return data using data transfer (DT) messages, ensuring function blocks across different devices operate in perfect synchronization. Devices are assigned data link layer addresses made up of a three-part structure: link, 16 bits, node, 8 bits, and selector, 8 bits. This allows a single Fieldbus segment to support up to 32 uniquely addressable devices, nodes, each capable of managing multiple virtual communication relationships, VCRs, through selectors. The node address defines the device itself, while the selector identifies individual communication endpoints or queues, known as DLCEPs and DLSAPs, within the device. To ensure quality of service, the DLL supports prioritized messaging. Messages are assigned one of three priority levels: urgent, normal, and time available, with urgent messages granted immediate transmission upon token receipt. The maximum allowed message size also varies by priority to ensure timely delivery: 64 bytes for urgent, 128 bytes for normal, and 256 bytes for time-available messages. This granularity ensures that high-importance data, such as alarms, is transmitted promptly. In addition to scheduled communication for function block linkage, the DLL supports unscheduled communication for tasks like diagnostics, configuration, and event reporting. During its token rotation, the LAS grants each device a pass token, PT, giving it a chance to transmit unscheduled messages. If a device has no data to send or exceeds its time window, it must return the token via return token RT, ensuring the system remains responsive and balanced. The data link layer also manages link maintenance. It periodically scans for new devices by issuing probe node PN messages. If a new device responds with a probe response PR, it is added to the LAS's live list, a dynamic list of all active devices on the segment. The LAS continuously monitors this list to maintain accurate awareness of network topology and to reallocate tokens as devices join or leave. Each device's participation in the scheduled communication depends on whether it holds the LAS role. Only one LAS is permitted per segment, but backup LAS-capable devices, Link Masterclass, monitor the current LAS and automatically assume its role if a failure is detected. This fault tolerance ensures that communication remains uninterrupted even in the event of a single-point failure. A crucial output of the DLL is the data link time, LS time, a timing signal broadcast by the LS to all devices on the link. LS time ensures that all devices are synchronized for function block execution, enabling precise alignment of control operations across multiple devices. This segment-wide clock is essential for maintaining coordination in distributed control architectures. The DLL utilizes a specific set of protocol data units, DLPDUs, to manage these operations. These include CD, compel data for scheduled publishing, DT, data transfer for sending data, PT, pass token, and RT, return token for unscheduled messaging, PN, probe node, type PR, probe response for device discovery, CL, claim LAS, and TL, transfer LAS for LAS role management, TD, time distribution for synchronization. In summary, the data link layer of Foundation Fieldbus is a sophisticated and deterministic communication framework that enables coordinated data exchange, distributed control, and fault-tolerant system management. Its disciplined, token-based approach ensures that all communications, whether for control loops, diagnostics, or configuration, occur in a timely, predictable, and interference-free manner across the shared segment. Specification for Foundation Fieldbus Part 6. Application Layer. The application layer of Foundation Fieldbus serves as the interface between the communication system and user-level functions, such as control, diagnostics, configuration, and data access. It is responsible for interpreting process commands, managing object behavior, enabling device interoperability, and executing standardized services. The application layer is split into two key sublayers, the Fieldbus Access Sublayer, FAS, and the Fieldbus Message Specification, FMS. Together, they form the essential framework for all functional interaction between field devices and host systems. The Fieldbus Access Sublayer, FAS, is responsible for managing virtual communication relationships, VCRs, logical connections between communicating applications. FAS provides three communication models that define how applications exchange data. Client-server model, bidirectional and request-driven. A client initiates requests, e.g., read, write, configure, and the server responds. This is ideal for manual operations, device configuration, and HMI interactions. Publisher-subscriber model, one-to-many periodic data transfer, used to link function blocks across devices in scheduled communication windows managed by the Link Active Scheduler, LAS. Source sync model, one-to-many aperiodic broadcast, primarily used for alarms and trend reporting, where the source sends data to multiple syncs using a common global address without expecting direct replies. Each device maintains one or more virtual field devices, VFDs, logical containers that house function blocks, system management agents, and device-specific services. VFDs are essential to organizing internal device capabilities and enabling secure, structured communication. Every VCR references a VFD, enabling access to specific objects such as parameters, alarms, or programs through unique object indices. The Fieldbus Message Specification, FMS, defines how messages are constructed and interpreted between VFDs. It models data as objects, each with attributes, behaviors, and access methods. Key object types include variables, represent analog or digital values such as measurements, set points, or outputs. Events, represent alarms or status changes. Domains represent memory areas used for program or parameter downloads. Programs represent executable logic structures like user-defined sequences or algorithms. Each object is identified by an index within the VFD and described using an object dictionary, OD. This dictionary includes metadata such as access rights, units, data type, engineering limits, and display format. Human-machine interfaces, HMI, and asset management systems use this data to render user-friendly views and enforce control permissions. FMS provides a rich set of services to interact with these objects. Variable services, read, write, report, and manage lists of variables. Event services, notify alarms events, acknowledge conditions, and enable-disable reporting. Domain services, download, upload bulk data to from field devices. Program services, start, stop, or reset programs inside smart field devices. OD and context services, access metadata and manage session-level interactions like identification, initialization, or disconnection. In scheduled communication, e.g. publisher-subscriber, the application layer relies on strict timing controlled by the DLL and LAS. Function blocks output data at predefined intervals aligned to the macro cycle, and LAS compels devices to publish at precise moments. Input parameters must be received before block execution, and output values must be transmitted immediately after. Alarm and event communication uses the source sync model and is typically unscheduled. Alarms generated by blocks are sent asynchronously to one or more global DLSAP addresses. These messages contain timestamp data and are repeated until acknowledged via the client-server model. Alarm priorities, Thresholds and hysteresis are all configurable via application layer parameters. The application layer also manages time synchronization through system management protocols. This enables consistent timestamping of events and coordination of function block execution across multiple devices and segments. Each device's internal clock is synchronized to the network-wide system time, ensuring accurate temporal alignment of control operations and diagnostics. Scalability and interoperability are central to the application layer's design. Devices from different vendors use standardized function blocks, parameter sets, and behavior models. Interoperability is achieved via strict conformance to the Fieldbus Foundation's specifications, validated through registration of device descriptions, DDs, and capabilities files, CFFs, which ensure consistent host behavior and user experience. In conclusion, the application layer of Foundation Fieldbus enables distributed intelligence, structured diagnostics, and vendor-neutral interoperability. It empowers smart field devices to execute control logic, report their condition, and respond to supervisory systems in real time, all through a consistent, deterministic, and highly standardized interface. This layer is the cornerstone of Foundation Fieldbus's value in reducing engineering complexity, enhancing diagnostics, and distributing process control intelligence.